In this part I want to talk a little bit about Synion and logarithmic and linear and many parts more. And before you skip to the next tutorial, because most people do that when they hear only the term Synion, then I encourage you to just follow along, because each part that I present here is part that fits finally into the big puzzle of Hdri. And I could make my life very easy. I could say, okay, take your DSLR, take several exposures, take only the time, no focusing or something like that during that time. Merge this all in one big Hdri file, save it as OpenEXR, use it in Cinema 4D, and be happy. Okay, so that would be the simple way. Would you feel really comfortable with that? That contains everything that we want to know. So why I'm talking about all of these formats? Because you get a very Sassi understanding about the formats, how we perceive light, and how to work finally on the end with all of that. So please follow along, get a good understanding about the whole subject, and make decisions on a pro level instead of just, oh, I got this somewhere on the web, I forgot where, and now I use it. Sorry, I screwed up the production. Okay, I hope I have teased you enough, so please follow along, and here we go. Just a little hint to the start why we use in R, G, and B most of the time linear formats or just formats that can contain everything beyond 100%. And when this here would be our 100% limit or border, and here we would have our 0%, so we have the range of our 8 or 16-bit integer formats normally, and we would say maybe we have here a red value of, that's roughly around 80%, and maybe the green would be in this range, and in the image the blue one would be here. So we get a nice color here finally, mixed out of RGB. So we do know something with this file. We add exactly the same amount to each of these files here. And here we get the same. So these are all the same, and we save this format out as 8 or 16-bit. This area here is clipped already, so we have no use for that. It's 100% and nothing beyond that. The green bar here is not hitting this 100%, so we have a little bit space. So we have red 100%, blue 100%, and green 100%. Now we open the file again, and we subtract maybe the same amount that we have added before from all these values here. So I make that a little bit bigger so you can see what I'm doing here. I subtract now this amount exactly from these guys here back. And you can see here with the stroke in the other direction, this is now the new level that we have. And here we go from there to there, and now we have a value that is exactly here. And you can see that we had before a complete different ratio between these three guys, and now it's more grayish. And if the green would have gone also over the top, this bar here would be even higher as well. And if all three are over the top, all three values would be the same now, which ends up in gray. And that is exactly what happens when you have to deal with nicely balanced highlights that nearly touch this 100% border, and then a little adjustment comes and it gets clipped, it's not there, and the next time you go a little bit lower, all of these values have the same level. And exactly this problem is more than often visible in CG footage that becomes then composed in a more or less bad way based on formats that can't contain these values beyond 100%. We could argue now that the composer could have started and convert first the files or save them out in a better format. But why not starting in the first place? And of course the same happens to you with the renderings. When we have those things going over the top, they get clipped, and the differentiation in the color values are more than limited. And so not a way to go. That is why we use 16 or 32-bit float. That's exactly where we have to go. An exception of this is of course given from the old times, and that is Cineon. And Cineon tries to do something that works more like film, and on the same level tries to figure out what is best for our perception. And I will start to explain that here in a sec. To understand all of that, we have to go first into the characteristic of a film stock, celluloid to name it. And again, here we had here our stops for the normal exposure of movies. It's not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as normal values. It's in stops. So each stroke here is double the amount of light. When I say film works pretty much in this way, then we have a characteristic curve that maybe many people know who deal with film on a regular basis. We have 3 areas here. That is one time the toe area, then we have here the middle area, and then the shoulder area. And I want to talk about all 3 of these, of course. The point here that we set normally in the middle part is given then when we want to have a normal look and feel to the movie. Of course, we can over and underexpose a movie to create a very specific look, and it changes dramatically when you do this very extremely. The toe area here is an area where we have all the dark values, but most of the time we set here our black point, which means we have 1 or 2% of reflectance, and that is then our black point. And we have darker values here, and we need a little bit space to have maybe all the noise and stuff like this inside of that area. And then we have here the middle part, and the middle part itself is very important, where we store everything. It's nearly linear in terms of stops, and we expose the movie there. There is our main interest, and there is the interest that we want to have for our perception. That's exactly what we see most. But if we ignore this area here, the highlights or the shoulder, then we run into something that looks more like the video from 10 years ago or so, with clipped highlights and everything else. And so this area here contains a lot of data, because the more we go to the right, the brighter the highlight becomes, and we are not really interested in super differentiated highlights. We need highlights to work with them. If we would just clip everything here, we would have exactly what I have explained before. So a tiny little differentiation here in this area is very important, and so we can dial in a nice rolled out highlight here. And remember, those curves here mean the more horizontally they get, the less differentiation they have for the output side. And when I have the input side here, I have a huge area that goes then here into something very small, like this here. Okay, so we can go now here and say, when we have a curve like this, and we capture the movie, we scan the movie, and I paint here just a frame into it. When we scan the movie, we get this pretty much in the same way as before, linear in terms of stops, and then we compress here more and more the highlights, and we compress more and more the darks here. We don't want to crunch them, we don't want to clip the highlights. And in this way, Cineon started to work. And I want to go into another explanation to give you more depth on that. When we go again with our horizontal line here from the graph, and we say this here would be the absolute black point, and then we go here towards the sun, more and more. And then we have areas here where we look maybe straight into a light bulb, and we have maybe here a candle where we look directly in a candle, and then we have in this area here that I mark now pretty much the area where our interest is. And this here is near to be infinite in terms of brightness values, at least from our perception. And you remember, hopefully, that we have a perception that works pretty much like a gamma curve. And you can read this in Charles Pynton's book or in many other areas. So when we want to create an output file to this side, we should have a lot of material inside of this, and then less and less from these super brights here. But we want to have a differentiation. We do not need a differentiation between 100,000 and 1 million in contrast, as we need maybe the differentiation between a candle and a light bulb. And this difference is maybe not as big as you think in terms of the difference between 100,000 and 1 million. It's maybe similar in ratio, but the steps between are way bigger. But we are not really interested in this one. We are more interested in this area, and we are highly interested in this. And then a little bit less in the dark areas again. So we should have something that works pretty steep here, and then goes flat out to this area and flat out to this. And then we have something where we have the perception of our eye satisfied. And we do not waste a lot of space here in our output file for the super bright highlights. So the idea was, of course, now how could a curve like this be described and how to make it very simple to make that happen. A reason why I talk about this is because it makes more and more clear that we need this stuff here, of course, but we don't need so much from it. But we need a lot of definition and ideas in this area. That means definition means resolution in 3 dimensions. That means x and y as a normal picture is, and in depth, that we can have a huge variety of tones here and not just 8-bit or something like that. And we want to have, of course, a very stable color space here, a reason why I talked about color profiles. The colors here shouldn't be clipped at all to get always the right color for the highlights, even if we always go along when the highlights are just white. But in the moment we use it for image-based lighting, the sun is never white. It has always some colorization and it changes over the time. So the typical idea that the daylight is 5500 Kelvin is not a stable datum. It goes from the morning to the day to the evening, and alone during the daylight it has a change. So we should take advantage of the dynamic range that we can get from anything. And that is why I'm talking about. Okay, let's have a look how the Cineon file works finally. And it's relatively simple in the moment you understand which idea is behind that. As we have seen, when I tried to fit a linear file into an 8-bit integer, we run into problems, and that was given by half stops. So 1 stop is already 50%. You remember that? I hope that was quick enough. And when we think about the darkest value here and toward the sun to this value, then we might say this is the limit here. That's already super bright, and I take this as a limit and I say we have not so much space, we use a 10-bit file, which is practically a standard in TV or for Cineon. For most Cineon files we have different variations in it as well. So we would have 1023 here when we start with a 0 here, so 124 at all, to make that clear. When we go now here with that value close to the sun, then our main interest area shrinks maybe to this part here, 200. and this would be here maybe 10 times that value. So in this area we have our main area for the stars, for the actors, for the buildings that we want to capture, and then all of that here is just wasted practically for light. That sounds not very clever, and so to take 90% of the footage or the files just for super bright highlights, I don't think so. And that was exactly the idea many decades ago from Kodak to create Cineon. But how can we do this when we want to have the 100% very big? So we want to expand this, and we want to have the 100 to 900 much smaller, maybe even smaller like this. The simple idea was given with a mathematical description. So we want to have values between 1, 10, 100 and 1000. And you might get already the idea. Each of these values equals 10 to 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. And that is the whole mathematic practically behind Cineon. So we move with these numbers the values along our gray values, and I'll show you in a second how. If we take our normal ruler or axis here from our graphs, and we say we want to have here 1000, just for the simplicity, it's 1023 normally, and we want to have here 0 or 1, whatever. I make it here pretty simple. Then we can say we would have here normally 500, 250 and 750. That would be a normal integer file. But now we want to have, of course, the value of 100 moved towards the 1000. And so we can also go here, and I draw here another axis into it, and we divide this here by 4. It's hopefully pretty exact. So 1, 10, 100 and 1000. So with our exponent we can move these values here. And when you take a look, and you have ever opened in After Effects, for example, the Cineon description, then 685 was always a number, and you might ask, where comes this from? And it's exactly this mapping here. And for the values of 90, for example, for the dark values, that is roughly here. That is then exactly mapped from this value, and you get something here, let's say 3. I guess this. Don't nail me on that. But so you know already how these numbers came together. And of course, these numbers here, 90 and 685, are not chiseled in stone. So sometimes you have a different film stock, sometimes you have a different look and feel that you aim to. So these numbers can change. But now the 0, 1, 2 and 3 from the exponents becomes mapped to this. And I can go now here between the 90 and the 685 and map the parts where I'm mostly interested in, where our eye has the most pleasure in it. I map them to a huge part of the whole file here, and that would be 1023 to be honest. And so we can take this inside the file, we map the data now on a wider area, and when we want to read this out again, we need only to know where was the black point set, where was the white point set, and when we have a floating point format and not an integer format, we stay with the whole bandwidth of that file. If we read this out to an integer, we get here our 0, we get here our 100%, and we lose maybe all the other data here, which is not really fun to have. Okay, so stay always, even with these wonderful ingenious tricks inside of floating point, when you get those files, Cineon these days is mostly in use as an export or import file when you come from a film scanner or when you want to have your stuff printed out on celluloid. So the reason why I talk about this, it's because inside of Cineon is a lot of technology that reflects the human eye and the perception that we have. And the whole series about HDRI and linear light workflow here has as main spine or back the human perception in mind. And of course, we want to create the best quality possible, and we need, of course, an understanding how all of that works in conjunction with the humans, because that's the target after all. And I hope this gave you a little bit more certainty when you get those files. Because HDRI was done, I think, the first time in 1815 with a split exposure, 1930 with film, and later on with digital cameras. It's not a new theme. And of course, to go always back in history too much is not nice. So I would think we are ready to roll now the production, and the theoretical part is, for now, over. See you in the next part.